Greetings everyone. It's time to talk about exponential functions. Okay, so whenever you hear exponential functions, you should be thinking exponents, right? That's exactly it. Notice in the setup of an exponential function, it's anything where we have some number a to the variable x power, right? And that's the key. The variable x is in the exponent. Then a is just some number, and depending on what a is, we categorize the different functions, right? So if a is anything between 0 and 1, we categorize that as a decreasing exponential function. And if a is anything greater than 1, we categorize it as increasing. Now I want you to notice what you don't see in those categories is anything negative. A itself will not be a negative number, okay? And also there's no equals on the zeros and the ones there. A will not be equal to 0, a will not be equal to 1, okay? A being negative is too interesting, and a being equal to 0 or 1 is not interesting enough. So these are the categories we're going to stick to, okay? Some other things to remember when doing these things is to remember some of your exponential skills, okay? Anything raised to a 0 power is 1, okay? Anything raised to a negative power gets reciprocated, and anything to a fraction power can be translated into a radical of some sort, okay? So here's an example of an exponential function. Y equals 2 raised to the x. Notice 2 is greater than 1, so this is going to be in the increasing category of the function here, okay? So what I've done is I've plugged in a few values so that we can talk about the x, y points for some of the major points of this function, okay? So notice, importantly, when I plug in 0, I get 1, right? 2 to the 0 power is 1. And that's important because that's literally going to happen on every basic exponential function, okay? As long as it's not shifted or anything like that, anything to the 0 power is going to be 1, right? And then, of course, from there, if I plug in 1, 2 to the 1 is 2, 2 to the 3 power is 8, 2 to the 10 power is 1024, okay? So it's going to increase as I let x become more positive, right? And that's this side of the graph right here. As I let x get more and more positive, y is going to explode in size. As you can see, by the time x is 10, y is already in the thousands. Okay, but on the other side, if x is negative 1, I get 2 to the negative 1 power, which is reciprocated to 1/2. 2 to the negative 3 is 1/8. 2 to the negative 10 is 1 over 1024. Okay, so what you'll notice is as x goes more and more negative, the y value continues to shrink. However, it's always 1 over something here, and that's to give you a hint. It never actually reaches 0, right? And that's this side over here. You can see that it gets smaller and smaller and approaches the x-axis, but never actually gets there, okay? So some major important features here are that it's asymptotic on one side, and then it's unbounded on the other, and it has this center point, okay? So the center point is 0, 1, and you have your horizontal asymptote, the x-axis right here. Okay, here's another example of an exponential function. F of x equals 3/4 to the x. 3/4 is a number that's in between 0 and 1, so this is going to be in the decreasing category, right? You'll notice again, 3/4 to the 0 power is 1, right? So 3/4 to the 0 is 1. There's that center point again at 0, 1, right? That's important. So then notice, as I let x become more and more positive, right? 3/4 to the 1, 3/4 to the 2, 3/4 to the 5th power. It's always some fraction where the denominator is larger than the numerator. It keeps getting smaller and smaller. It's actually decreasing on this side this time. And then if I let x be a negative number, they get reciprocated, right? For example, 3/4 to the negative 2 gets reciprocated to being 4/3 to the positive 2, which gives you 16/9 here. And the further negative you go, the larger the value will get. And so you get the unbounded side on that side this time. So key features, again, the center and the horizontal asymptote are the same, but it's just in the reverse order on a decreasing function. When we're doing exponential functions, typically we go with the increasing style. That's mostly the ones that we run into. And later on, we're going to talk about how I can transform the functions, much like we've done back in the earlier chapters with shifting and reflections and things like that. So typically, we stick with the positive one as our major default graph. And then I can always turn this into a decreasing one with a reflection anyway. Okay. Let's talk about graphing these functions and then also throwing in a little bit about domain and range. Okay, so let's look at this first one over here. I have 3 to the x plus 2 power, right? Now remember, 3 to the x is a normal exponential function. And the thing to notice is that the plus 2 is on the inside with the x. And remember what inside means, right? Inside with the x means it's a horizontal effect. And the addition and subtraction typically is opposite, right? Whatever causes that inside to be 0 is the new center x value. So this happens to be a shift 2 to the left. So to accommodate that on the graph, I'll remember that my center point used to be at 0, 1, right? So my center point used to be at 0, 1. If I shift left, then that's going to be the same as subtracting 2 just from the x. So my new center point should be at -2, 1, which is right here. I didn't shift up or down, so that didn't affect any of my y-centered things, such as my horizontal asymptote. My horizontal asymptote is still going to be the x-axis. Okay? So then my graph is going to be an increasing exponential going through this center point. So I hug right here. I hug the asymptote, which is the x-axis, right up until I get to that center point. Then I peel away from the asymptote a little bit, just peel away. As soon as it hits that center point, that's when the pattern changes and it just skyrockets. Like that. Okay? Now the domain on these, on all these exponentials, you should always expect the domain to be all real numbers. And what this is saying is that any exponent can be used as an input here. Any number can be used as an exponent. That's what that really means. Now, of course, the range on these right here, that's 0 to infinity, right? That's my range. Notice a parenthesis on the 0 because it is an asymptote. Okay, next. 5 to the x plus 4. The plus 4 here is outside. So remember, that means to shift up. Since it's on the outside, it's a vertical effect, and plus means to shift upward. Okay, so my center point in that case, right? It used to be 0, 1. Shifting up by 4 means that I'm going to be adding 4 to this guy here. Just the y value. Okay, so then my new center should be 0, 5. What about my horizontal asymptote? It used to be y equals 0. Well, remember, shifting up affects the y values. So that also is going to become something new. Y equals 4 in this case. So here's what I do. I go up 4. I put a horizontal asymptote there. And then my center point, which in this case is 0, 5, right? It's going to be right here. And then I draw my graph from there. It's going to hug right here until it gets close to that center point, in which case it's going to start peeling away. And when it goes through that center, then it takes off. Right? And in this one, notice my range values is now 4 to infinity. Right? Because 4 is the bottom value there. It's going to go up forever. Is it possible to have both shifts in one problem? Sure, just like any of the other transformations that we've done. This is a shift to the right 1 and down 3. Okay? So, what's going to happen to my center point for this one? It starts out at 0, 1. If I shift it right 1, right, that's plus 1 on the x, and down 3 on the y, I now have the point 1, negative 2 for the center. Now what about the horizontal asymptote? It started out as y equals 0, and it shifted down 3. So my new horizontal asymptote and my new center are right here. Let's draw those out. So down 3, and I have a horizontal asymptote there. Okay, then my center point is now at 1, negative 2, which is here. And so then I have to draw my increasing exponential function, which is going to hug the asymptote on this side. It's going to peel up to the center, and then it's going to take off, like so. Okay? So notice the range on this one. Is negative 3 to infinity, right? From bottom to top. So shifting works pretty much the same as any of the other functions. You just have to be careful of where you're reading the shift from. All right, so on the other side of things, we also still have reflections. And a negative directly on the x, remember, is a horizontal effect, so it's a horizontal reflection. So that's what I would label here, right? This right here gives me a horizontal reflection. So what does that mean? Well, normally my increasing graph, right, does like this. So if I do a horizontal reflection, that's a left-right reflection, it's going to just do this. It's going to flip this way. So it's going to look a lot like a decreasing exponential because of it. My center and my asymptote stay the same in this case. It's just going to do this. My center point is still at 0, 1. And my asymptote is still the x-axis here. Okay? Now over here, I have a negative 11 to the x. The negative is not connected to the 11. If I wanted it that way, I would put a parentheses, but then it wouldn't be in the categories that we've talked about already. So I'm not going to do that. The negative, however, is on the whole function, which if you remember back from one of the earlier chapters, a negative of a function is a vertical reflection. Right? So this right here gives me a vertical reflection. What does that mean? Well, 11 to the x, right? Exponential function that's increasing this way. A vertical reflection would do this. It would flip it up and down ways, right? Like this. So it's still going to hug the asymptote, but instead of going up, now it's going to go down and to the right like that. Okay? So I still have my same asymptote, but here's worth noting, the center point starts out at 0, 1 like always, but doing a vertical reflection changes the 1 to a -1. Think about that for a second, right? My normal center point is above the x-axis. If I reflect on the x-axis, it's going to put it at the bottom, okay? So my center point goes from 0, 1 to 0, -1, and my asymptote is still the same. So I essentially get this shape. There's my new center point at 0, -1. And as soon as it hits the center, it takes off, but in the negative direction this time. Okay? So notice the horizontal reflection, the range is the same as before. 0 to infinity, right? But if I do a vertical reflection, my range is now -infinity up to 0. Okay. So let's do one that's a mixture of several of these things, right? Let's piece this thing apart right here. I have a 4, but that's not part of the original function, right? There's no x's in there. Then there's a negative. That's going to be a reflection of something, right? 2 to the x plus 3. Well, look, there's 2 to the x, right? That's an exponential function. The 3 is added directly to the x, so that's going to be a shift left. Right? The 4 is positive here, and it's added on the outside. So this is going to be a shift up. And then the negative is on the outside of the function, like this one. So that is a vertical reflection. Okay? Before I draw this one, another little side note. Do you notice how I'm pretty much just drawing all of these shapes the same? Even though the base keeps changing, right? Base 5, base 3, base 9, base 7. They pretty much all have the exact same shape, okay? And I'm being a little bit, not caring about that. And that's because I'm not really putting a scale too much on my grid, because this is supposed to be efficient and fast shape graphing, okay? If you actually wanted to put 2 of these on the same grid, you would notice a huge difference in how one of them takes off a little faster than the other, or shrinks toward the asymptote a little faster than the other. But unless you're going to compare them like that, you're really not going to notice the difference, and we can pretty much just throw the shape on a grid for our own understanding purposes. Okay, so with that in mind, let's throw this one on a grid. Let's start with the center point, right? My center starts out at 0, 1. Always do your reflections first. Horizontal reflection doesn't affect the center. Vertical reflection does. I happen to have a vertical reflection, so I take care of that first. That means my new center starts at 0, -1. Now I have to shift it. Left 3, so -3 to the x, and up 4, so +4 to the y. That's going to give me -3, +3 for my new center. This is my actual center point of this graph. Okay? Now what about my asymptote? Horizontal asymptote starts out at the x-axis, y equals 0, but we're shifted up 4. So my actual asymptote is going to be y equals 4. Let's graph this guy. Okay, y equals 4 is my asymptote. Okay, and my center point is -3, 3. So let's put some marks on here. -3 up 3 is right here. Okay, And then I just need to think about what's actually been done here to make sure I have the right shape in my head, right? Because it could hug either side of that asymptote. We shifted, we took a normal, increasing exponential, right? We did a vertical reflection, so it looks like this. Then we shifted it left and we shifted it up. So it should still hug on the left side and peel away on the right side, right? Should still look like this. Give or take. Okay? So much better than I could draw this. I could pull it up on a GeoGebra screen for you. So why don't you go take a look at that for a second. So here we are in the rectangular system, and what I'm going to start with this time is just the basic exponential function, y equals 2 to the x. And again, we graphed this one earlier, and I want you to pay attention to the fact that the center point is at 0, 1, and it has the asymptotic behavior on the left-hand side. Okay, so to build it up to the last function that we were talking about, the 4 minus 2 to the x plus 3, let's do it one step at a time. So I'm going to start with the the vertical reflection, right? If I do a vertical reflection by putting a negative on the outside, that's going to make it do this. Notice the center does actually flip to the point 0, negative 1 there. From there, I'll do the shift to the left of 3, right? Which makes your center move from here to here. So it's now at negative 3, negative 1. And then from there, I'll do the shift up of 4 to finish it out. So it goes from here up to here, right where the center was where we calculated it the last time, at negative 3, 3. Okay, also note the asymptote has been shifted as well. It is at y equals 4. Quick side note. You wouldn't have had an excuse to really run into this value in any calculations or anything before this, but now that we're hitting exponential calculations and functions, it is important to note that there is another special number out there. I'm sure everyone has heard of pi. It's very, very popular, 3.1415926, right? That guy. Completely irrational. Okay, well, a much more modern special number that comes up in lots of different natural applications, even the growth in pine cones and trees and even people, okay, is this number that we call the natural number. Okay, it's symbolized with a lowercase e, which is why we never use little e as a variable. Okay, much like pi got his own symbol, this one got the letter e, right? For the guy who really discovered it and made it useful is Euler, right? Anyway, so E is approximately 2.718-ish, okay? It is an irrational number, just like pi. It does go on forever with no pattern. And if you want to see a longer version of it, you can pick up any calculator, and they should have an E to the power button, right? In the calculators that we use in these courses, there's a button on your calculator that says ln, and above that you'll see an e to the x or e to the power button. Okay, so if you hit second or shift or whatever and you hit that button, you'll get an e to something, and if you hit e to the 1, you'll get actual e. We'll be using that particular calculation quite a lot. Okay, so the number you'll see a lot of times will appear as a base of an exponential function. So just remember that this e is not a variable, it's not actually a letter either. It's supposed to represent this special number. And it's going to come up in a few formulas, okay? So just keep that in mind. Okay, so something else that we want to kick off in this section is some of the basic solving that comes with exponential equations, right? So not functions, but equations this time. It still means that you'll have a variable in an exponent, okay? So 3 to the x equals 9 is a good introduction to this. And what it is I'm going to use this special property, which basically goes around the solving part, that the real meat of it. I don't have to do a lot of complicated solving with these particular problems. It's analogous to using factoring to solving quadratics, right? Factoring goes around the problem of quadratics and solves it, quickly, but it doesn't always work. That's exactly what's going to happen to us here. It will work with these particular equations, but it won't work all the time. But it does get rid of a lot of the complicated issues of exponents, okay? So watch, here's how I'm going to do it. Basically, to have the one-to-one property, the way we're going to use it, I just want to have some base on both sides to be the same. If I can get both sides of my equation to have the same base, then at that point I can conclude that the exponents must be equal. And that's because exponential functions are one-to-one functions. There's only one way to calculate an exponent. So if two bases are the same, then the exponents have to be equal there. Okay? So right here, 3 to the x equals 9. Right now the bases aren't the same, 3 to the x and 9 to the 1. However, I can rewrite 9 as 3 squared. And now that 3 and 3 is the same base on both sides, I can conclude that the exponents must be equal. Therefore, x equals 2. Okay? Now, of course, that's a really simple equation. You didn't really need to solve it because you can guess from your times tables. 3 to what power is 9? Oh, that must be 2, right? That's just to get you through the door here, okay? Let's solve these two equations using this property. 8 and 4 are obviously not the same base, but I need to think of, can I rewrite them as something to a power and the same thing on both sides? And the answer is yes. 8 is 2 to the third power, and then it's raised to the x. And then 4 is 2 to the second power, and it's raised to the 2x minus 1. Okay? Now at this point, the only thing you have to remember is how to simplify some exponents, right? Don't forget that when you raise an exponent to another exponent, you just have to multiply those two exponents. So in this case, I'll have 2 to the 3x, 3 times x, right? And then here, I'll have 2 to the 2 times 2x minus 1. All right. Well, now the bases are the same on both sides. Remember what that means. If the bases are the same, I can set the exponents equal to each other. So in this case, I am now 3x is equal to 2 times 2x minus 1, which is now a linear equation, and I can just solve for x. 3x equals 4x minus 2. Subtract 4x from both sides, I get negative x equals negative 2. So then x must be 2, right? And if you're not sure, plug it back in and let's see. That would be 8 to the 2 power, right? 64. And then here, 2 times 2 is 4 minus 1 is 3. 4 to the 3 power is also 64. So that's definitely a good solution. Okay, let's try again. 1 over 3 to the x and 27 to the 5 minus x. I have to write both sides as the same base. Okay, well, don't forget, fractions I can write with negative powers, right? So right here, this is the same thing as 3 to the negative 1 to the x. And 27 is 3 raised to the 3 power to the 5 minus x. 1 power raised to another is multiplication, so that's negative x, and 3 raised to the 15 minus 3x. Don't forget that that's multiplied by the whole thing, so I distribute. The bases are now the same, so I can solve it like so. Negative x is equal to 15 minus 3x. Because the base is the same, I can drop them. I add 3x to both sides, so 2x equals 15. and then I divide by 2, so x is 15 over 2. Okay? All right. Solving exponential equations with the one-to-one property. Okay? Now the only caveat is it doesn't work with every single exponential equation. Easily you could muck this up by just one number being different, right? If this were 26 instead of 27, well then I couldn't rewrite it as a power of 3 very easily, right? So this only works for very few, kind of like factoring with quadratics, right? But when it does work, it's really nice, and it's only a few steps. One other application that comes up in this section is we begin to talk about compound interest. And the idea behind compound interest is it's not just normal, everyday, simple interest. Simple interest is what you would expect on a schoolyard from a child where they said, oh, you owe me such and such interest on whatever money I loan you, and it goes up by $10 every week, right? If it goes up by the same amount over over different times, then that's just simple interest. Compound interest is more realistic interest that you would see like from a bank or from adults, right? If you gain interest on something, that now becomes part of the account in question, and then that new money also gains interest the next time it's calculated. So it's interest on top of interest, which is why it's called compounded interest, okay? And it's much more of an intricate formula for compound interest. And I have the two main formulas that you'll need here, okay? So for most of the applications, if it just says compounded yearly, compounded quarterly, compounded whatever, you'll use this top formula here. If you see the words compounded continuously, then you switch to this other formula here, okay? Let me talk about both of these for a second. The A in there is the after amount, right? The amount that happens after the time has passed. P is for principal, the starting value, principal, not the PAL principal, right? Okay. R is the rate. Rates are typically given in percentages. Don't forget, percentages are communication devices. The R rate here needs to be the decimal or fraction of the percentage, okay? Not the actual percentage number. So if you're given 55%, you would put 0.55 for R, right? Or 55 over 100. I prefer the 0.55, okay? T, of course, is time. Usually for money, time is measured in years. However, if you're going to do things with applications and say credit cards or things like that, sometimes those can be measured monthly, which, side note, that's how credit cards can really sneak up and get you, because it is compounded monthly, not yearly. Okay, so be careful with credit cards for that sense. Okay, now you'll notice the capital N is just in the top formula and not in the bottom one. Okay, and that's for the reason of that being the number of compounds. For example, if it says compounded yearly, then N is 1, right? Once per year. If it says compounded monthly, then N would be 12, right? 12 times per year would be monthly. If it says compounded continuously, then you switch to this other formula where there is no N. It's all included in the formula. Notice the E, right? That's that natural number. It's part of that calculation. Anything that's compounded continuously is going to be involved with this growth rate involving the natural number E, okay? Now you'll also hear me refer to this formula as the shampoo formula. It just helps people remember it. PERT, P-E-R-T, like the shampoo PERT, right? Okay, so this is your normal formula, this is your shampoo formula, and it just depends on the application, right? Okay, so here's what we'll do. We're going to talk about this example here, okay? And it's going to be the same principal and interest rate and everything as it goes up, but it's going to be different types of compounding, okay, so that you can get a feel for how these things are set up. So I've got this savings account, and right now when I start it with $6,570, right? Well, that'd be nice, right? Grows by 12% every year, okay? So calculate the amount that's in the account after 4 years, but 3 different types of compounding so that you can get a feel for this, okay? So let's say that they tell you, oh, it's 12% compounded yearly. So in other words, n equals 1, right? So this is pretty much a calculator formula. I'm just going to have the formula, I'm going to have all the values, but I'm really just going to punch and crunch it, right? A is going to equal to 6,570 times 1 plus, R is the rate, so that's 0.12, divided by n, which is 1, raised to the power of 1 is n again, right? N is in both places, times t, so t is 4. You'll notice I wrote this in calculator speak. This is exactly what it would look like as you're punching it into the calculator that we use, and most of the other ones that are out there too. So 6570 times 1 plus 0.12 divided by 1 is 0.12, and then raised to the power of 4 times 1, which is 4. Okay, so the value that I get here is that A is approximately equal to 10338, and this is money, so I'll put 0.02, rounding to the nearest cent, right? Okay, so if the interest rate is just compounded once per year, in other words, the interest is calculated one time in the year, and then every year the same after that, after 4 years, this is the amount that you would expect to see in that account. Okay, now let's do quarterly. Quarterly just means that I'm splitting the year into 4 pieces and doing the interest each time. So that means in this case, quarterly means that n is 4. So A in this case would be equal to 6570 times 1 plus, same interest rate, but now it's divided by 4, and it's raised to the power of 4 times the time, which also happens to be 4. Okay, so notice the n value is what's changed here only. Everything else is the same. So I have this, same as before, and now I'm going to divide by 4, raised to the power of 16. So notice this time, A is approximately 10542.92. It's not the same, is it? In fact, it's more. Because remember what this is. This is compounded interest. If I'm compounding it, if I'm calculating it more often, then that's giving you more money, which as it grows also gains its own interest, right? So the more often you add in money, even if it's a little sliver that's smaller than before, right? Every time you add in more money, that's more money gaining interest. So even though it's the same percentage and it's the same beginning amount, because I'm chopping it up and putting money in more often, it's going to grow larger, okay? So then what's the absolute maximum of this? That's continuously compounding. In other words, every little split second it's in there, it's constantly putting a little bit of interest in. That's going to be the most that you can do. And that's what this other formula is. To do the continuous compounding, I use the shampoo formula over there. So that would be A equals 6570 times E to the power of, now remember your calculator has a special button for E, and I'm going to put parentheses, R times T. Well, my R is 0.12 times T, which is 4 years. So that's what I'm going to punch in here, 6570. Second, and the ln button gives me the e to the power. Then I have 0.12 times 4. And so here I get that A is approximately 10671. Oops, sorry, got those backwards. 10617.61. And you'll notice that it is slightly larger than before even. That's the most that you can get out of increasing the compounding there, okay? Now, of course, we'll be hitting more of this as the sections go by for this particular topic, but for now, these are the ones that you need to practice and, sort of get through the doorway here, okay? stay tuned for our next one on logarithmic functions.